So what I'm going to do is to introduce it by looking at an example of how calculus might be useful, run through that with you, and then give you some rules to write down that we'll refer to. Basic, very straightforward rules they turn out to be, and then we'll look at examples, which will probably take us to the end of what I want to do on it today. Okay. So the first thing to ask about this is how is it useful? Why do people use differential calculus? Well, probably, I think maybe Mr. Wilding would agree, the single most useful branch of mathematics to an engineer is probably differential calculus, I would say. Okay. Let's look at an example taken from the textbook. So you would find it in the algebra section and also comes up in the calculus section in the textbook. We're going to look at this. If we cut up a piece of sheet metal to make an open top box like this, then there's some algebraic expressions written on here. If we look at this sheet of metal, it's 12 centimeters wide by 20 centimeters long, and written on here is x. So if I'm going to make a box out of here, I need to cut out these corners so you can fold up to make a box. Okay? And this value of x determines whether it's going to be quite a wide, shallow box or a narrow, tall box. As I change the value of x, I'm going to change the shape of the box. Agreed? For a given value of x, what's this expression here telling me? Which is about this length from here to here. George. And say that again. Right, so why is it 20 minus 2x? Exactly right. I've got the full length, which is 20 centimeters, subtracting 2 lots of x. Does that make sense? And look at the algebra. We've been talking about algebra. Look at that expression, Jack. Okay, 20, the whole thing, minus 2 lots of x. So you can see, can't you, why the width is 12 minus 2x. Okay. Now, if I wanted to write an expression for the volume of the box, tell me the equation for the volume of a cuboid. Exactly. Length times width times height, or whatever terminology you want to use. Write down for me, using these algebraic expressions in here, a formula to find the volume of the box. That's an expression for the volume of the box, isn't it? This part is the length, if that's what we want to call it, the long bit. This is the width of the box, and that's the height, length times width times height. And we know, so we've now got an algebraic expression, a formula involving algebraic expressions to find the volume of the box. And if somebody told me what x was, then I could calculate the volume of the box by plugging that in. Okay. If we change x, we can change the size of the box, as we've said already. What value of x gives the maximum volume? That's what we're after. If I think about this box, whether it's wide and shallow or narrow and tall, okay, the volume will change. And what we're after in a manufacturing process is finding what value of x will maximize the volume we can get out of the box. We want to use it to pack stuff into, so we're after the maximum volume to make the best use of the materials we've got. To answer questions like this, and in fact other areas where we're after maximum values and things like that, we use differential calculus. So let me just point this out to you, and then I'll pause it so you can write it down if you want. Differential calculus, any function, and what we've just written down is a function for the volume of a box. Any function can be differentiated. So that's like the verb. Differential calculus is what we do, and we differentiate things. You know, it can be differentiated. And it gives a new function. So it's a different function to the original one. And it tells us this. This is the key thing that differential calculus does. It tells us the rate of change or the gradient, in other words, of the original function at any point that we're interested in. It tells us the rate at which things are changing, and for an engineer that's often a very useful thing. As soon as things start to move, we're interested in the rate at which these things move, and that's when differential calculus becomes useful. So if I just pause, how does this help us to find the maximum value of the box that we're interested in? Let's look at a graph of the original function. Okay. So what I've done is, this function that we came up with here, look, for the volume of the box, I've plotted an autograph. There it is, look. So you got it exactly as I'd written it, Elliot. Okay. The volume of the box. You didn't see these notes, did you? You didn't look ahead, did you? No. The volume of the box. I typed that into autograph. And if you remember autograph, it recognises x as a variable, but not v, so I'd have to type in y equals, and it would give me y against x. So here's x. This is this increase in the length x, so I'm cutting out of the corner of the box. This is plotting the volume as we change x. Note that there's a maximum value for the volume. It looks as though it's around about 260, 270, okay? Whatever unit we're talking about. And x looks as though we get this value at around about 2.4, 2.5, something like that, okay? Notice also that when x is 0, we've got no height to the box at all, and so the volume is 0, what we'd expect. There's a point here at which the volume drops to 0 again. And then, weirdly, the volume goes negative. Well, that's not going to happen in the real world. So something else engineers often do when they look at a function is they actually decide at what point the function no longer behaves like anything in the real world. This is the mathematical function plotted, this one. As far as the math is concerned, this isn't the volume of a box, it's just v against x, and so it carries on plotting x to infinity. The curve carries on up, okay? And also for negative values of x down here. What we have to decide is which bit are we interested in. We're interested only in this bit, aren't we, Jack? Okay? When the volume is positive value. Okay, so what does calculus allow us to do? Differential calculus? The rate of change or the gradient. So when x equals 1, that's the gradient at that point. I could draw a tangent to the curve at that point, give me the gradient. X equals 2, the gradient's a bit less. Positive, quite a large positive value for x, a bit smaller. If I differentiate it, and we'll talk about how to do that, I'd be able to find out what's that gradient at that point. Saves me having to draw a triangle and do all that jazz, okay? And that's difficult anyway because it's always changing, and that's the problem with calculus. Here, when x equals 4, now it's a negative gradient. What's special about the gradient, though, when the volume is maximum? What can I say about the gradient at that point? It's 0. Who said that? Right, 0. If I plot the tangent at that point, draw the tangent to that point, look, there's a horizontal line. And what's the gradient of a horizontal line? 0. So what we do is, if I want to find the maximum value of this box is, I differentiate it to find the function that tells me the rate of change, and then I find out when that's 0, and it gives me the maximum. It gives me the value of x that gives me the maximum, and that's what I'm going to do now. So, to find the maximum value, I differentiate it and find the point when this is 0. And again, I'll pause if you want to write that down.